Hi, and welcome to this short video explaining the concept of reactance for inductors and capacitors. Reactance is defined as the opposition to the flow of charge and current in an AC circuit, which subsequently results in the continual interchange of energy between the source and the magnetic field or electric field created by the inductor or capacitor respectively. The reactance of a component is given the symbol X and has a value that is dependent on the frequency of the alternating current or voltage waveform. These reactance values of capacitors and inductors, alongside the resistance of resistors, form what is called the total impedance of an AC circuit, which is equivalent to the total resistance of a DC circuit and can be used in the modified form of Ohm's law, V equals I ZT, where ZT is the total impedance found from the formula ZT equals R plus J multiplied by the reactance of the inductor minus the reactance of the capacitor. To find the reactance of inductors and capacitors, we need three things: the inductance of the inductor, measured in henries, the capacitance of the capacitor, measured in farads, and the frequency of the alternating waveform, measured in hertz. The reactance of the component can hence be found from XL equals 2 pi multiplied by the frequency times the inductance of the inductor, or XC equals 1 divided by 2 pi times the frequency times the capacitor capacitance. From these formulas, the frequency dependence of reactance is evident. It can be observed that by increasing the frequency, the inductive reactance will increase and the capacitive reactance will decrease, as shown in the graphs on the screen. So, do inductors and capacitors in AC circuits behave just like resistors, you may ask? Doesn't this violate the idea that ideal inductors and capacitors only store energy? Well, yes, but actually no. You see, AC problems require complex solutions, and while both resistance and reactance are measured in ohms, when measuring total impedance, reactance includes the imaginary term J, which is equivalent to 1 unit, angle 90 degrees in polar form. For inductive reactance, this term is positive J, and for capacitive reactance, this term is negative J. The net result is that for reactive elements, the current through them and the voltage across them are out of phase by 90 degrees. This means that the power consumed by them is positive for half of the sinusoidal period and negative for the other half. The net result is that the average power being delivered to a reactive element, inductor or capacitor, over one period of the waveform is zero. This can be interpreted by understanding that the same amount of energy flows into the reactive element as there is flowing out of it. During the charging phase, these elements store energy, consume power, and during the discharging phase, they release their energy, acting as a power source. For resistors, on the other hand, both the voltage and current are in phase, and so the power term will always be positive. This is because V and I are positive and negative at the same time as each other when their waveforms are in phase. Hence, resistors only ever dissipate energy and do not act as an energy storage device like capacitors or inductors do. And that concludes the video. Thank you for watching.